Hello, everyone. I'm meteorologist Sean Sublette, and welcome to Across the Sky, our National Lee Enterprises weather podcast. Lee Enterprises has print and digital news operations in more than 70 locations across the country, including at my home base in Richmond, Virginia. I'm joined by my meteorologist colleague, Matt Holiner in Chicago. Our pals Kirsten and Joe Martucci out of the office today. Our guest this week is Zeke Hausfather, a climate scientist very deep into the data and has a wealth of information about how much warming is taking place globally. And we really wanted to pick his brain about what's going on in the oceans this year in particular. There has been so much buzz, Matt, about how hot the oceans are right now. So we wanted to kind of get into some of the reasons for that.
Yeah, that's the headline, I think, grab people's attention. Of course, as soon as there was those 100-degree temperature readings off the coast of Florida, then immediately all the headlines were hot tub water, and everybody knows what a hot tub feels like. And it's like, yeah, I don't think the ocean should just be naturally that hot if it's, not being artificially heated. But I mean, it is just getting warmer. But I also think that sometimes, and that's the challenge, where there's, still doubt, unfortunately, that comes up with climate change, because then certain things get exaggerated because there is something, because they're also following that, lots of headlines about the thermohaline circulation shutting down. And what I liked in our discussion coming up with Zeke was he really dived into that and explained how likely it is and what's really going to happen, because immediately all the memes of the day after tomorrow came, and it's like, oh, if the ocean current shuts down, it's going to be a global ice age. And, whoa. Let's talk about what's really going to happen, how likely the circulation shutting down really is. That was just one of the things that we discussed about with them. But it's always good to come back to the experts that really know what's going on, rather than just people just throwing stuff out there on social media, because there's still a lot of bad stuff on social media.
Yeah, and he talked about, if you've never heard of the thermohaline circulation, sometimes it's called the AMOC. It has a lot of different nicknames, but he talks about what that is, why it's important. He also addressed that 101-degree water temperature, some things that are going on with that. And we just talked about where climate change is now and how much warming we should expect. So lots to get to with our conversation with Dr. Zeke Hausfather. Let's go right to it.
Michael J. for Hope for the Warriors. Started back in '06 at Camp Lejeune. Military families witnessing the effects of war on their loved ones. Now, almost 20 years later, they've aided over 53,000 service members, veterans, and families with confidential, high-quality behavioral health care services at little or no cost to post 9/11 vets and their families. Over 91% of every dollar donated goes directly to the programs. If you're as concerned about our heroes as I am, go to hopeforthewarriors.org.
Dr. Zeke Hausfather is the climate research lead for STRIPE and a research scientist with Berkeley Earth. He's a climate scientist and IPCC author whose research focuses on observational temperature records, climate models, carbon removal, and mitigation technologies. Zeke also serves as science contributor to Carbon Brief and was previously the director of climate and energy at the Breakthrough Institute, the lead data scientist at ESSIS, the chief scientist at C3AI, and the co-founder and chief scientist of Efficiency 2.0. And on top of all that, in his spare time, whatever spare time he has, he runs a very excellent Substack with Andrew Dessler over at Texas A&M called The Climate Brink. So we are just pleased as punch, as Mama used to say, to have Zeke Hausfather with us on Across the Sky. Thanks so much for joining us, Zeke.
No worries. Excited to be here.
All right, so let's jump right into the whole oceans thing. This has been on top of everybody's climate weather minds for several weeks now about how warm the oceans have been this year with regard to the longer term record. So before we get into the specifics about why they're so warm this year, talk a little bit about, I guess, the metadata, the data sets that we are using and why we are so confident about making such a statement about the oceans being as warm as they are right now.
Sure. So we've collected ocean data for a long time. It was, in fact, back in the 1840s, there was an international convention to standardize the collection of temperature data from ships, in part to better understand shipping routes, weather conditions, to make ship journeys more predictable. In fact, the reason we start global temperature records, like those we produce at Berkeley Earth or NOAA's or the UK Met Office record in 1850, is because that's when we start getting enough ocean data to at least, with reasonable errors, estimate global temperatures. So in the early days, we used to measure ocean temperatures by throwing wooden buckets over the sides of ships, pulling them up, sticking a thermometer in, and writing it down in the captain's logbook. Funny story, that actually had some biases, because as you're pulling a bucket up the side of a ship, it evaporates. Some of the water evaporates off the top, and that cools the remaining water in the bucket. And so you actually get slightly cooler temperatures with buckets. Around World War II, we switched primarily to ship engine room intake valves, where the water goes through the hull of the ship to cool the engine. These are steam ships or, more modern diesel ships. And it turns out engine rooms are a little warmer. So you have some biases there in translating from buckets to ship engine rooms. And then starting around 1980, we really transitioned in large part to automated buoy systems that, there's thousands of them. They float around the ocean. They send data up to satellites. And in more recent years, since the 90s, we have satellite radiometers that can measure the ocean skin temperature directly. And it turns out that all these different sets of instruments largely agree with each other. You have to correct for biases when you switch from one to the other, of course. But if you do that, you get a pretty good, consistent, high quality record of ocean temperatures since at least 1850. And certainly, we have incredibly good records, for the last few decades when we have satellites and buoys and ships and these awesome robots called Argo floats that float around the ocean and dive down to 2,000 meters and sample all the ocean heat content and other variables on their way up. So we're really in the golden age of climate data, particularly when it comes to the ocean today.
Real quick, before we talk a little bit more about this year, just for my own thing, in my own mind, I know the Argo floats have become very popular recently. Off the top of your head, an approximation, to a first order of magnitude, about how many of these Argo floats are kind of out there right now?
So the latest number I heard, and it's a couple years old at this point, but it was about 3,500 Argo floats. And they're pretty well distributed around the ocean. There's a few areas they don't get, so they're not great at going under sea ice. In fact, scientists have figured out a pretty cool hack for that, where they actually put thermometers on the top of seals' heads, like wild animals, and they dive under the sea ice to get temperatures there where the Argo floats can't go easily.
Wait. They put a thermometer on top of the head of a seal.
Yep, a couple hundred seals have thermometers on their heads, and they're taking measurements. They're very small thermometers.
I'm guessing this is a very tiny electro radio transmitter. Yeah. It's not something like they're just this big liquid and glass thermometer sticking on their head.
No. There's a little transmitter off on the seal's head that's pretty small and unintrusive, but takes measurements when the seal's under the ice, and then sends it off to a satellite when they get back to the surface. And they track the seals and take it off their head after a year or so, and then rotate new seals into the seal temperature monitoring core. So that's one area that scientists have had to fill in the gaps a little bit. The other is the deep oceans. So our current Argo network mostly goes down to about 2,000 meters or 6,000 feet or so. Below that, we haven't had as many measuring systems historically, but there's a new deep Argo program that's trying to fill in some of those gaps.
That's amazing. Matt, do you want to jump in with anything?
Yeah, I'm still wrapping my mind around seals taking temperature readings for us. If
you Google it, there's some very, very adorable pictures of seals with little instruments on their heads.
I'm sure. My question is, as far as the coverage goes, we're talking about, it seems like in many locations, sea surface temperatures on the rise. I mean, a combination of El Nino but also in the Atlantic, seeing the sea surface temperatures on the rise. But I'm trying to kind of get into more of the details about it. Instead of just saying sea surface temperatures are on rise everywhere, are there certain locations where we're really seeing a particular rise more so than other parts of the planet?
Yeah. So historically, over long-term changes, some parts of the ocean are warming slightly slower than others. Like the Southern Ocean is always a bit wonky because it has, a lot of overturning circulation and a lot of deep mixing. There's a weird cold patch off the southeast of Greenland that may be related to a slowdown in the thermohaline circulation, though there's a lot of debate around that. But historically, the oceans have generally warmed at similar rates. This year, though, we've seen this really crazy warmth in the North Atlantic that is far beyond the level of warming we're seeing in other ocean basins. And so that's been really remarkable. And a lot of people have, focused on that as a, very unusual thing and tried to look at different potential explanations for it.
And I kind of want to follow up with that thermohaline circulation, because immediately when you talk about that, I think of the movie The Day After Tomorrow and how the ocean current shut down. And then suddenly there was this mass blizzard, we went into an ice age. So can you talk about the likelihood of this ocean current shutting down and what would actually happen if it did happen? And is it going to be at the scale of the day after tomorrow?
Sure. So I'll start with the likelihood, and then we can talk about the day after tomorrow. So scientists have historically thought the likelihood of a shutdown this century is quite low. Most of our climate models show it slowing down, in part as you have a lot of freshwater runoff from Greenland. So to back up a little bit, the way the thermohaline circulation fundamentally works is that as waters travel north in wind-driven currents in the Atlantic, more and more of the water at the surface evaporates, which means that what's left over gets more and more salty because the salt stays when the water evaporates. And as it gets salty enough, it gets denser. And once it gets dense enough, it starts to sink. And so that drives one of the big ocean circulations is the sinking of saltier water in the North Atlantic. But it turns out if you start melting Greenland really quickly, you dump a bunch of fresh water into the North Atlantic, and that can make it less salty, which then makes it not sink, which then can slow down and eventually shut down the circulation. So climate models historically have not expected a shutdown this century, though they have expected a slowdown. In the last few years, there's been a couple more speculative papers suggesting that the models might be missing some things and that the possibility of a shutdown this century is higher than previously anticipated. That said, this is still a very much on the bleeding edge of science, so I don't think any of us can say with confidence what's likely to happen this century. We just can't rule out a shutdown. If a shutdown were to occur, it's important to emphasize this doesn't mean the Gulf Stream is shutting down. The Gulf Stream is driven by the rotation of the Earth and winds. It's not going anywhere. But the thermohaline is still very important for heat transfer, particularly to Northern Europe. And so if we were to see a shutdown, we would see temperatures drop, over, coastal Northern Europe, probably by, 3 or 4 degrees centigrade on average. Some parts around Iceland, you might even get to like 8 degrees C drop compared to current temperatures. Not quite day after tomorrow levels. We're not going to see the oceans freeze or, New York become a winter, permanent winter Arctic. We're really talking more about the European side of the North Atlantic where the biggest effects will be felt. And over the long term, the effects of warming for most countries in Europe would outweigh the cooling associated with the shutdown. It'd still be bad. It would affect rainfall patterns a bunch in problematic ways. It would mean it was a lot cooler, particularly in places like the UK. It wouldn't be a good outcome. But at this point, we're still very much digging through the data and modeling and trying to get a clear picture of what exactly is happening with it and what is likely to happen as Greenland melt picks up.
Yeah, I know there was a lot of buzz about this in the last couple of weeks with that. I think it was a Nature Communications paper that came out to kind of reignite that conversation. Back to the North Atlantic and the overall global oceans. Well, obviously climate change is a big issue. It's kind of the overall background driver. But talk a little bit about a couple of these other things that have kind of bubbled ahead or forward on top of that. Obviously El Nino is going on, but there's discussion about an underwater volcano in the South Pacific, how fuels and shipping lanes in the North Atlantic might have changed. Could you just talk a little bit about those other kind of mitigating factors and how much they may or may not be playing a role?
So let's start with the volcano and then talk a bit about sulfur. So there was a very large eruption in Tonga in 2022 of an underwater volcano, and it affected the climate not by providing heat to the oceans, because the amount of heat provided by volcanoes to the oceans is actually pretty negligible on a global scale compared to the amount of heat that's being trapped by greenhouse gases. But what this volcano did that was really weird compared to most volcanoes we see is it shot an incredible amount of water vapor incredibly high into the atmosphere. It put about 150 million metric tons of water into the stratosphere, which is a part of the atmosphere that doesn't have much water vapor in it usually. And that matters a lot for the climate because water vapor itself is a strong greenhouse gas, but because water vapor, rains out if you get too much in the atmosphere, it doesn't last for long, so it can't really accumulate. But the stratosphere is a little different because there's so little water vapor up there. If you put water vapor up there, it doesn't rain out. And it can stay in the stratosphere for a lot longer than you'd have water stay in the lower parts of the atmosphere. It takes a couple years to clear out, water vapor added to the stratosphere. And so while most volcanoes actually cool the planet by putting sulfur dioxide into the stratosphere, if they're really big volcanoes, this one unusually actually likely warmed the planet by putting a lot more water vapor than it put in SO2. Now, there's been a couple papers on this that estimate that globally the magnitude of the effect is probably somewhere in the range of 0.15 watts per meter squared. It's a very wonky number we use to estimate the amount of energy trapped in the Earth's system. But to convert that into numbers people might understand, we're probably talking about somewhere in the range of, 5/100ths of a degree centigrade of warming associated with this volcano, so 0.05 C, which is not nothing, but is not nearly as big as the excursions in temperature we're seeing globally.
Is there a limit to these temperatures? Is there a threshold, is there a certain level where the oceans can't get any warmer? Or are we going to continue to just let, now next is going to be 101, 102? I mean, is there a threshold about a limit to where we're going to go? And just kind of talk about how exceptional that 100-degree temperature really is.
Yeah, so I think the provisional record was actually 101. Now, granted, it was in an area of very shallow water with a lot of biomass in the water that can absorb sunlight. So those areas do get in the high 90s pretty frequently, but this was very, very high. And we've seen, high 90-degree temperatures around the Florida Keys a lot this year. So I think that's, another sign of this exceptional thing that's happening in the North Atlantic in terms of temperatures. As far as how hot it can get, there's not a functional limit that says when the oceans reach, 102 degrees, they don't increase anymore. But what you do have is this sort of relationship where the hotter a surface is, the more heat it radiates. And it actually radiates heat at the 4th power of temperature, to get a little wonky. So you have this Stefan-Boltzmann equation at work. And so what that means is that the hotter it gets, the more heat it's giving off to the atmosphere, the harder it is to warm up further because it's giving off more and more heat as it gets hotter. And so there ends up being a bit of a negative feedback, as we call it, a countervailing factor of it's just hard to get things that are already hot hotter compared to heating up cool things. And so that does help provide a bit of a limitation to quite how hot it can get.
I guess on some point it's a limit of diminishing return once it gets to a certain temperature profile, I'm assuming.
Yep.
All right, good deal.
It's one of the reasons why climate change doesn't run away as easily on Earth, which is a good thing.
Yes, we like to tell people the planet's not going to turn into Venus anytime soon. We're going to take a quick break. We'll have more with Zeke Hausfather when we come back on the Across the Sky podcast. And we're back with Zeke Hausfather, a climate scientist with numerous organizations, does a lot of work, also has a wonderful Substack for folks who aren't very deep into climate science. He runs that with Andrew Dessler over at Texas A&M called The Climate Brink. I want to go back to the current state of the oceans. We talked a little bit about the underwater volcano in the South Pacific, but there's been a lot of buzz on how fuels used in shipping traffic in the North Atlantic may have played a role. Can you talk a little bit more about that?
Sure. So when we think about climate change happening more broadly on Earth, we know that the greenhouse gases we're putting in the atmosphere are warming the planet, but it's not the only thing that humans put in the atmosphere. We also put a lot of sulfur dioxide into the atmosphere. It comes as a byproduct of burning fossil fuels primarily. And sulfur dioxide, it turns out, is actually a strong cooling effect on the climate. And that's through two different mechanisms. The first is what we call the direct effect, which is that it's very, sulfur dioxide particles are very reflective. So some sunlight hits those particles in the atmosphere, bounces back up to space, and it just dims the sun essentially at the surface. Some people call it global dimming in areas that are very polluted because of that. The second is the indirect effect, where sulfur dioxide particles and aerosols in the atmosphere can serve as cloud condensation nuclei, and so can increase the amount of cloudiness in regions where you have a lot of SO2. And you see this, in contrails from planes and ship tracks from ships that are going over the ocean, where you see clouds forming in the wake of the ship because of all the SO2 that's coming out of its stack. And it turns out those sort of clouds are good at reflecting sunlight and cooling the surface. So historically, we've used a pretty dirty fuel for ships. It's sort of the fuel that's left over from oil distillation that's too dirty to burn on land because it would fall afoul of our clean air rules. We actually call it bunker fuel. It's this very tarry, goopy stuff that's left over at the bottom of the stack after oil distillation. And it turns out it has a very high sulfur content. And the reason ships are allowed to burn it is because they're mostly far from shore. And you have less air pollution concerns in the middle of the Atlantic or middle of the Pacific. But unfortunately, ships are still using it near port, and a bunch of studies in recent years have found that it has some pretty nasty health impacts on people who live near shore. There's one study that estimated that something like 60,000 people worldwide die prematurely a year because of ship-based sulfur pollution. And so because of that, there's been a big push over the last decade to try to phase out sulfur in marine fuels to reduce the harmful human health impacts of burning it. But about 10% of all global sulfur emissions come from ships. And in the year 2020, the International Maritime Organization put in a new set of rules, essentially reducing the amount of sulfur that ships could emit by 90%. So if you think about 10% of all of our sulfur emissions globally coming from ships, we reduce that 90%, you get, somewhere around a 9% reduction in all global aerosol SO2 emissions, sulfur dioxide emissions. And that's a pretty big deal. In the recent IPCC report, our best estimate was that aerosols cool the planet by about 0.5 degree C. And so if you have a 9% reduction in 1 year going forward in all of aerosol emissions, 9% of 0.5 degree C is still a pretty big number. It's like 0.05 C. And so there's likely roughly that level of additional warming globally from reducing these aerosol emissions. But the thing is, these ships are not emitting globally. They're emitting in particular regions, particularly the North Atlantic and the North Pacific. And so in those regions, we expect a much bigger climate effect from removing these aerosols, reducing the amount of ship tracks and cloudiness in those shipping corridors. So my colleague at Berkeley Earth, Robert Rode, he did an analysis where he looked at essentially what's the difference between the temperatures we're seeing over the shipping tracks after the year 2020 when they phased out this fuel and the other parts of the ocean. And he found that after 2020, those regions warmed about 0.2 C more than the rest of the global ocean. And so we can say, the sort of shipping track regions in the North Atlantic and North Pacific have probably had, at least 0.2 of a degree warming in the last few years because we phased out we phased out the high sulfur fuel. We required low sulfur fuel.
All right, so I'm going to turn this over to Matt. Before I do, I have two quickie follow-ups. One is for my own mind. When we think about SO2 being kind of reflective, are you saying the SO2 molecule or as an aerosol with other impurities? And two, what is the general lifetime of SO2 and those aerosols in the atmosphere before they finally settle out?
The reflectivity is primarily the sulfur molecule itself, but it is in an aerosolized form when it's sort of moving around the lower atmosphere, the troposphere. The lifetimes we're generally talking about are in the order of weeks. It falls out pretty quickly in the troposphere. If you were to put it in the stratosphere, as we see with like large volcanic eruptions like Mount Pinatubo, there you have a residence time in the like short years. Probably about half of it falls out in the first year, but there's a bit of a tail before it all falls out of the stratosphere. That's why we saw something like 0.5 degree C cooling globally the year after Mount Pinatubo erupted, is because it put so much SO2 up into the stratosphere, and then it hung around for a couple of years after that, suppressing temperatures.
And while we're looking at these other issues that are playing into this, another story, and that's what I want to kind of like focus on. Is it a completely separate story, or is it tied together? Is the plastic pollution problem in the oceans? We keep hearing about the increasing amount of plastic in the oceans, and of course, there's lots of negatives associated with that. But I wonder if there's been any research at all. Is the amount of plastic in the ocean having impact on the sea surface temperatures, whether lowering them or raising them, or does it seem to not have an impact and it's just a separate environmental issue?
It's a great question. I haven't seen any research on albedo effects of plastic. I think that even places like the Great Pacific Garbage Patch, which is a very evocative name, it's not that dense. It's not like if you're going in a boat through there, it's just the surface of the ocean is covered with plastic. It's like there's pieces here and there. So I'm sure it has an effect because seawater is dark and absorbs sunlight. Plastic is generally not as dark as seawater and reflects sunlight. There probably is on the margins a cooling effect, but I suspect it's not particularly strong. But it is a big issue, obviously, for wildlife, and I'm sure a lot of your listeners have seen, David Attenborough's documentaries of like seabirds on remote islands with plastic in their bellies, and these tragic pictures of. Yeah.
Let's think forward a little bit. We have had globally some progress in terms of emissions, at least regarding coal. Coal is in decline, at least in a lot of places. My understanding is that China's throwing everything out there, solar and coal and everything. But the demand for coal isn't as high as it used to be. Having said that, we still are burning a lot of fossil fuels that aren't necessarily coal. So some of the worst case scenarios we imagined 15, 20 years ago don't appear like they're going to be coming to fruition. It doesn't mean it's not going to be bad, but when we look at where policies have kind of evolved to now, how much warming, now in the pipeline should we kind of expect in the coming several decades? I know it's a broad question, but let's just kind of attack where we've come, how far we've come in the last 10 or 20 years, and how that might translate forward.
Yeah, so a decade ago, things looked really dire for the Earth's climate in terms of where we were heading. Global coal use had doubled over the course of a decade. China was building a new coal plant like every 3 days. And the idea that the 21st century could be dominated by coal, where we'd double or triple our emissions by 2100, didn't seem that far-fetched. Today we're in a very different world. Thankfully, clean energy has gotten cheap. Most of the new energy being built worldwide is renewables today, or at least clean energy that's low carbon. And global coal use has pretty much flatlined since 2013 or so. Which also means that global emissions of CO2 have more or less flatlined over the last decade. The problem is that when I say emissions have flatlined, it sort of makes you think, oh, that means global warming is stopped too, right? But it doesn't quite work that way. The world is going to keep warming as long as our emissions of CO2 remain above zero. That's really the brutal math of climate change, is that it's not enough just to stop emissions from increasing. You actually have to get them all the way down to zero to stop warming. If we just flatline emissions like we are today, what that means is that warming continues at the rate that we've been experiencing for the last decade or two, 0.2 C per decade or so. And so if you look at a bunch of different assessments of where we're headed today, and these have been done by the International Energy Agency and the United Nations Environmental Program and groups like Climate Action Tracker, they all more or less agree that we're headed for a world of around 3 degrees C, maybe slightly below, by 2100. That compares to a world of 4 or 5 C that seemed possible a decade ago. And so that does reflect progress. We've bent the curve downward of future emissions. We've made some of these really, really catastrophic high-end scenarios a little less likely. But a 3C world is still a really bad one. I mean, we're experiencing a lot of severe impacts of climate change already in terms of heat waves and wildfires and extreme precipitation events just at 1.2 degrees today. And so if you more than double that, it's a pretty terrible world for a lot of people and for a lot of nature too. The natural world is a really tough time adapting to very rapid changes in temperature, like we'd see. So 3 degrees is certainly a lot better than where we're headed, but it's by no means anywhere close to where we want to be. The good news for me, at least, is that the fact that we have started to make some progress means that it's a lot easier to imagine worlds where we actually do make more progress. We continue these positive trends and accelerate them, and we actually do manage to limit warming to at least below 2 degrees by the end of the century. I think, unfortunately, 1.5 degrees is probably in the rearview mirror at this point, unless we, do some crazy scenario where we pass it and then remove, ridiculous amounts of carbon from the atmosphere to bring temperatures back down. But certainly, I think you could say that limiting warming to 2 degrees or below 2 degrees is quite possible from where we are today. It would involve getting all of our emissions of CO2 to zero by 2070 or so globally, which is a big lift, but it's by no means impossible.
And it's good to hear a little bit of good news, because it is definitely by far mostly bad news when it comes to climate, but it's good that we're going in the right direction. Hopefully the trend will continue. I want to kind of look in the short term, though. We're in this El Nino event, and that's what's contributing partially to the high sea surface temperatures that we're seeing and the high global temperatures in general. But looking ahead to 2024, how's this El Nino going to play out, and what impact is it going to have on 2024's temperatures?
Sure. So there's a growing strong El Nino in the tropical Pacific right now, that's really developed rapidly in the past few months. What was interesting is that we switched quite quickly from an unusually long La Nina event. We called it a triple dip La Nina because it's what he's sort of kept starting to come out of La Nina conditions and then dipping back in. And that happened, 2 more times after the initial La Nina. But because we rapidly transitioned from La Nina conditions to El Nino conditions, it's really added a lot of heat, particularly to the oceans. We expect the current El Nino event to continue and strengthen through the end of the year. and stay fairly strong at least through early to mid 2024. There is some differences in the various modeling groups looking at El Nino. The dynamical models, the more like climate models, tend to predict a stronger El Nino than the statistical models, which are more trying to infer based on the statistics of past El Ninos, what's likely this time around. And that divide is actually kind of remarkable this year compared to most past years. I, for one, probably would bet on the dynamical models because I think they capture more of the underlying processes. Like statistics only bring you so far. But in terms of the effects of the El Nino, it's going to bump up global temperatures as well as sea surface temperatures for the remainder of 2023. It means that this year is now the odds-on favorite to be the warmest year since records began since 1850. But it's really going to have a big effect next year. And so 2024 is likely to be even warmer than 2023 for the year as a whole. And we've seen historically that there tends to be a bit of a lag between when El Nino conditions peak in the tropical Pacific and when the global temperature response to that El Nino event peaks. And that lag is about 3 months. So 3 months or so after you hit peak El Nino conditions, then you have the peak surface temperature response globally across the land and the oceans. And that's been a pretty consistent relationship for the past, 80 years or so at least. So if that holds this time around, and the El Nino peaks in the, near the end of 2023, we expect sort of the biggest push to be on early 2024 temperatures.
So what we'd probably be looking at is a particularly warm end of winter and into the spring months. So I guess, the groundhog would be predicting an early spring might be what we're seeing in a lot of places, would be kind of an idea if this El Nino plays out as it's expected to.
Yeah, that's globally. Like El Nino has very specific patterns of heat and cool associated with it that may affect different regions differently. So you can't necessarily say like every part of the planet is going to be warmer because of the El Nino. It really ends up depending a bit. Like in California, we tend to get a slightly cooler and rainier weather in El Nino years, for example.
Right. So the overall pattern of what the impacts that El Nino brings is going to be overriding. But looking at the big picture, that's probably when temperatures are going to peak, would be late winter, early spring.
Yep.
All right, let's go back south again. I was looking at a plot today. I think you actually shared it about the Antarctic sea ice and how it is way below the last 45 years of records. Is there anything that we should take away from that? I mean, it's kind of a frightening plot. Or is it just one of those things like we really don't understand the Antarctic ice surrounding the continent as well? It's a signal, but we really shouldn't panic about it. I mean, what is your take when you see that kind of graphic of what's going on in the sea ice around Antarctica?
So it's definitely disconcerting. Like we've never seen anything like this in the historical record for Antarctic ice. At the same time, Antarctic sea ice has always been a lot more complicated and unpredictable than Arctic sea ice. Arctic sea ice, if you look at the data since 1979, which is when we first got like good satellite coverage to get high quality Arctic wide records, it's pretty much been going down consistently. Like some years are higher, some years are lower, but there's a very clear linear downward trend as the Arctic warms. Antarctica, at least through 2020 or so, was bucking that. Sea ice was increasing overall in Antarctica between 1979 and 2020. And there was a lot of work among scientists to explain why that was. Part of it has to do with prevailing wind patterns. Part of it has to do actually with the hole in the ozone layer over Antarctica, which has a cooling impact for the region. And so, it was always sort of a much bigger question mark of the climate impacts in Arctic sea ice compared to the Arctic, where it's much more straightforward. And so then we get to the last 3 years where that slight upward trend in sea ice in Antarctica suddenly reversed. It went down, pretty far in 2021 and 2022, and then 2023 hit, and we really, have been at unprecedented lows for the entire year, particularly now when sea ice should be growing rapidly and it really isn't. And so there just needs to be a lot more work by scientists to untangle, what are the drivers of this? Is it unusual warmth in Antarctica? Is it warm sea surface temperatures or air temperatures? Is it changing wind patterns that might be breaking up sea ice in ways that, we haven't seen before? Like part of the problem is we only have a record going back to 1979 for this region. And so it may well be that there's some modes of variability that could lead to big shakeups in Antarctic sea ice that might have happened before, but just hasn't happened since 1979. So, I don't think we can rule out that it's primarily caused by human activity. And certainly we expect long-term, as the Antarctic region warms, to see less sea ice there. But this is so far below what we'd expect that I think, we need to take a close look at it and figure out all the different potential causes.
And before we wrap up, every time we get someone on, talking about climate change and what we're seeing out there and all the various issues, I think what it always comes back to is, people read all these articles and it's all doom and gloom, but then it's like, well, what can I do? What can I do to make an impact? I think when it comes to the oceans, this is particularly unique because we don't live in the oceans, we're on land. And so people kind of see the impacts of what's happening on land. And I think so many of us are ignorant about what's going on in the ocean. So if someone's listening to this and is alarmed and wants to make an impact and wants to, again, looking at the whole issue, but let's just look at the oceans itself. What are things that individuals can do if they want to see these sea surface temperatures not be as extreme? What are some proactive things, instead of people just reading this and saying, well, what do I do? What is your answer for when somebody asks that question?
So I think and it's funny to use the word comforting in this environment, given everything happening. But one of the more comforting findings out of the recent IPCC report was that if we can get emissions all the way down to zero, warming will stop. There's not a huge amount of warming in the pipeline that is inevitable, which means that ultimately, like, humans are at the driver's wheel here, or in the driver's seat. We get to determine, based on how much fossil fuels we burn over the next century, exactly how warm it gets. We're sort of stuck with what we have today regardless. But we can determine, if it just gets a bit worse or if it gets catastrophically worse. And that's mostly on us in terms of how quickly we reduce our emissions of CO2 from burning fossil fuels and how quickly we switch to clean energy alternatives. So as an individual, obviously it's a huge problem that requires collective action globally, but at the same time, you can do a lot by supporting clean energy technologies, because the more people who buy things like heat pumps or electric cars or put solar panels on the roof, the more the price of those technologies goes down, and the more other people can afford to adopt them. We've really seen that with electric vehicles, which 10 years ago were incredibly expensive and today are actually cheaper to own than a gas vehicle over the lifetime. Similarly, solar panels were 9 times more expensive a decade ago than they are today. And a big part of what's driven those cost declines is just economies of scale. More and more being built, people learning how to build them more cheaply. It's not fundamental breakthroughs in the physics, it's learning by doing. And so individuals making decisions to, pay a small premium to get clean energy in their personal lives, a heat pump, an electric vehicle, a solar panel, it is an important way to make it easier for other people who might not be as motivated to be able to adopt those, or just make it the default because it's the cheapest thing for people to do. I think the other thing I'd say is that at the end of the day, individuals voluntarily taking action can only take us so far. We need a stronger policy response by governments to make clean energy cheap and to hold polluters to account. And so I think, at the end of the day, one of the most impactful things you can do on this issue is vote. Tell politicians what you think, because they're going to have to help us address this.
Zeke, I think you hit the nail on the proverbial head there. Nobody can fix this all by themselves, but collectively we can make a lot of progress, and there's a lot of good reasons to be optimistic. Before we let you go, in addition to people reading your stuff on Carbon Brief and the Substack, where else can people find your work if they're not true wonks, or they're not policy wonks, or they're not deep into the science? Where else can people find what you have to say?
Yeah, so you can always follow me on Twitter or whatever it's called this week,
Right.
or on Threads, which is the new Meta-owned Twitter competitor. If you can also just read the coverage of climate that's going on in places like the New York Times, the Washington Post, or the BBC. It's all quality, and they talk to me occasionally, and a bunch of other climate scientist peers of mine who also have great insights in this stuff. So I'd say it's hard to find good discussions of climate on TV these days, but if you turn to the news, it dominates the headlines, and a lot of it is really well written and really good.
Yeah, one of the things that we've seen in polling is that people trust climate scientists, not so much people on TV. So that's why I always try to refer people directly to you, to Andrew, to Catherine Aho, those kinds of folks. Zeke, again, thanks so much for joining us. We appreciate it, and we hope that we get a chance to talk to you again soon.
Definitely. It was great to chat.
Looking beyond the atmosphere, here's Tony Rice with your Astronomy Outlook.
As the number of Starlink satellites has grown in recent years, more than 4,500 as of the last launch, so have the concerns about their impact to astronomy. You see interesting things in the night sky? They're really dim. and this requires long exposure photography, and that can be spoiled by these desk-sized satellites as they streak through the images. SpaceX did respond in recent years to these concerns by re-engineering the satellites themselves, reducing their reflectivity. And that new design, it will replace the entire fleet faster than you might think. According to Aerospace Corporation's Center for Orbital Reentry and Debris Studies, an average of 2 Starlink satellites deorbit each week, after a few months to a few years in orbit. But those changes are not really helping radio astronomers, like those at the Low Frequency Array Telescope in the northern Netherlands, who recently detected electromagnetic radiation from Starlink. All satellites, they have electronics on board that do release a small amount of electromagnetic signals, about as much as a TV. But radio telescopes are very, very sensitive. They're able to detect a cell phone on the moon. And if radio astronomers are seeing interference from 4,500 Starlink satellites, they're growing concerned about the impact that the planned 42,000 will have on the study of stars, galaxies, and black holes. Elsewhere in the sky, look for Jupiter shining brightly in the pre-dawn sky this week. And in the evening, look for Mars low on the western horizon. It'll settle up alongside a sliver of moon on Friday evening. Look a few degrees below, and you'll find Mercury. That's your astronomy outlook. Follow me at RTP Hokie for more spacey stuff like this.
That is so much good information, Matt. I mean, every time I talk to Zeke, I've talked to him 2 or 3 times before this, and I've been following him on Twitter, and you've heard me just kind of going on and on about the Substack. But he has so much good, actionable information. He's able to put so many myths to rest very quickly. And I could just talk to him all day long, but a lot of wonderful information about where we've come and where we're going. And he's got the data to back it up.
Yeah, it really is a fascinating discussion because so much of the focus is on land and what people are experiencing, but the majority of the planet, 70% of the planet, is the oceans, and they're absorbing a lot of heat and they're getting warmer as well. And when you're calculating these global temperatures, we talk about, this is the warmest year on record, which 2023 seems to be on track to do so. It's not just all the thermometers on land that we're calculating that. We're using all of these buoys to measure the temperature of the oceans. And that has a big impact. And that's why the fact that we're having an El Nino, it's an El Nino year when, already we're talking about sea surface temperatures just getting warmer and warmer. But during El Nino, they get even warmer than normal. And so that's what's going to contribute to seeing why 2023 is going to be so warm. And then it was also interesting how we're kind of teasing ahead to 2024. There's potential for 2024 to be even warmer because we're especially going to start 2024, it seems, so warm, and how even if El Nino starts to wind down, the lag in the global temperatures, because it has a global impact, will continue. So that's going to be something to watch. It was disheartening to hear that about getting even warmer. No. But at the same time, I did like where he did bring back, it's good to find the positives where we can, where it looks like those most dire predictions for what could happen, not to play it down, so not to let people's guard down, because he emphasized, 3 degrees of warming would still be really bad. But if we're going in the right direction, maybe avoiding that 4 or 5 degrees of warming by 2100, at least that's progress. So let's, but not let our foot off the pedal. Let's keep working. Let's see if we can bring that trend down. How about 2 degrees instead of 3 degrees? The more we can do, it's good to get some good news, but remember that 3 degrees is bad because we're already seeing what less than 1.5 degrees is doing, and it's not good.
Yeah, and that's 3C, which is 5.5 Fahrenheit. So we always have to remember that sometimes we get deep into the science and we kind of fall into the metric system, which is great. I love the metric system as a scientist, but a lot of people aren't as familiar with that. So yeah, 3C, that's about 5.5 degrees Fahrenheit. And I was also very grateful that he went back and talked about how we know what the oceans were 150, 175 years in the past when we had some ocean temperature records directly, but now we get so much of it from satellites and these cool Argo floats. Spend a little time and Google Argo floats because they're really, really cool pieces of equipment to help us see what's going on into the oceans. Matt, next week we've got, football season's coming. So let's go back on land, right? But we're into August now, and football practices are full tilt at this point, getting ready for opening day in a few weeks. And it's still hot. So we're going to talk to to Douglas Casa at the Corey Stringer Institute up there at the University of Connecticut and talk about the impact of heat on football players. It can be a very sneaky killer, unfortunately. So we're going to talk to him about that and some of the best practices to keep our players safe so we can enjoy what they do later on in the fall. Anything else, buddy, before we take off?
Yeah, and I'll also be interested in the impact of folks on the stands, because I've been at some awfully hot late August, early September games in Texas, and especially if it's a middle of the day game. I mean, the crowd is impacted as well. Of course, the players absolutely the most, but the crowd as well. So that'll be an interesting discussion. And then also, we're going to promote it again. If you ever have any questions for us, weather questions, things you'd like to hear us discuss, ideas for the podcast, shoot us an email, podcast@lee.net, or just a comment on the show. We'd love to hear from you.
All right, that all sounds good. All right, with that, we are going to wrap for this week. So for Matt Holiner in Chicago, meteorologist Sean Sublette in Richmond, Virginia for Lee Enterprises, thanks so much for listening, and we will talk with you again next week.